graph the rational function f of x is equal to -2 divided by x minus 2. So let's take this opportunity to review some of the important features that you should always be looking for before plotting your graph of a rational function. And the first thing that you want to identify is, what's the domain? Where does this function exist? So we have a rational function here, so we know that division by 0 does not exist. So we are going to set that denominator, or the bottom, not equal to 0, and solve for x. So we have our denominator is x minus 2, cannot be equal to 0. And solving for x here, we are going to add 2 to both sides of this equation. We see minus 2 plus 2 cancels itself out to 0, leaving us with x cannot be equal to 2. So we can make the conclusion here that therefore x can be any real number our little hearts desire, except 2. So if we wanted to write this in interval notation, that's negative infinity up till 2, united with the interval from 2 to positive infinity. So we'll keep this domain in mind. The next thing that you're always going to want to find when graphing a rational function are any vertical asymptotes. Now, vertical asymptotes are closely related to the domain. Recall that your vertical asymptotes are the zeros of the denominator. So since our function f of x is already simplified, we can simply take that denominator, x minus 2, and set this equal to 0, which is the same thing that we saw above with the domain. So this is letting us know that there is a vertical asymptote at the vertical line, x equals 2. The next thing that we're always going to want to be checking when we're graphing rational functions are the horizontal asymptotes. So with our horizontal asymptotes, we're going to be comparing the degree of the numerator to the degree of the denominator. So here we are given the rational function y is equal to -2 divided by x minus 2. Now we can equivalently rewrite this as -2 times x to the 0 power. And that's all divided by x to the first minus 2. So here we are comparing the degree in the numerator to the degree in the denominator. And so since we can see here that 0 is less than 1, that the degree in the numerator is less than the degree in the denominator, a horizontal asymptote exists at the y value, or the horizontal line, y is equal to 0. So this is an invisible line that our graph won't cross, as long as we don't have x-intercepts. Which brings me to the next thing that we should always be mindful to check when sketching the graph of a rational function. And that's the x-intercepts. And so we recall here, the x-intercepts is where the graph is crossing the x-axis. So we would set y equals 0 and solve for x. So we're checking here, is the graph of the rational function ever going to cross the horizontal asymptote? So we have the given rational expression, -2, divided by x minus 2, and we set this equal to 0. Now, to solve for x here, we are going to multiply both sides by this denominator, x minus 2, to simplify, remove that fraction. So we see x minus 2 divided by x minus 2 cancels out to 1, leaving us with -2 equals 0. Wait a second, does -2 ever equal 0? No, this is a contradiction. So -2 is never equal to 0, and we can conclude that therefore there are no x-intercepts for this graph. So the graph of our rational function is never crossing the x-axis. Now, the next thing we want to be sure to identify when graphing rational functions is the y-intercept. So this is where the graph is going to be crossing the y-axis. So here we're going to set x equal to 0 and solve for y. So we have y is equal to -2 divided by 0 minus 2, which simplifies to -2 divided by -2. And we know negative divided by a negative is producing a positive value. 2 divided by 2 leaves us with 1. So we have a y-intercept at the ordered pair 0, 1. Beautiful. Now, in addition to these features, to these 5 features here, to make sure that we are sketching a really accurate graph of this rational function, let's take this one step further and plot a few additional points on the domain. So let's create a table of values to plot some additional points. Now, we'll keep in mind here, the first thing we found was the domain, that x is an element of the interval from -infinity to 2, united with the interval from 2 to positive infinity. So let's now create this table of values and plot a few points around or within each of these intervals. So we have the x column, we have the next column is for our function values, that's -2 divided by x minus 2. And then our third column will be for the solution points, our ordered pairs. So we know, again, this function does not exist when x is equal to 2. So let's choose some points that are smaller than 2, like 1 and 0. Beautiful. And let's also choose some points that are greater than 2, like 3 and 4. So here we go. When x is 0, hey, we already found this. This is our y-intercept. So when x is 0, we know that y is 1. Now when x is 1, let's plug this in. So we have -2 divided by 1 minus 2. So that leaves us with -2 all over a minus 1. Negative times a negative produces a positive. So this is positive 2. And so we can now incorporate that third column here for our solution points, the ordered pairs x, y. So we have the first point, the y-intercept, 0, 1. And the second ordered pair we have is 1, 2. Now, when x is equal to 3, we have -2 divided by 3 minus 2. So we have, this is leaving us with -2 over 1, which is a beautiful final answer of -2. So another solution point on this graph is the ordered pair 3 minus 2. And last but not least, we have when x is equal to 4. This will be -2 divided by 4 minus 2. So we have -2 all over 2, which simplifies to -1. So we have the solution point or ordered pair for -1. So we have everything that we need now to sketch a really beautiful graph of this rational function. So last but not least, we are officially ready to sketch this graph. So let's begin by considering the coordinate plane. So the first thing that we want to do when we're sketching this graph is draw dotted lines for the asymptotes. So we know that we have an asymptote at x equal, or a vertical asymptote at x equals 2. So I'm going to incorporate a dotted line here, or a vertical dotted line at x equals 2 to imply that we have a vertical asymptote here. Now we also have a horizontal asymptote at y is equal to 0, or the x-axis. So we can incorporate a little dotted line here onto our x-axis to indicate that we have a horizontal asymptote here when y is equal to 0. Beautiful! Now, we also know that we have a y-intercept at the ordered pair 0, 1. So there it is, the ordered pair 0, 1, our y-intercept. We have a solution point at the ordered pair 1, 2. Beautiful. And we also have two additional solution points. When x is 3, y equals -2. So there's our point 3, -2. And last but not least, when x is 4, y is equal to negative 1. So in order to sketch the graph now, we need to connect these ordered pairs with a smooth curve. Now, keeping in mind that these curves cannot cross the vertical asymptotes nor the horizontal asymptotes in this case. So we'll extend them out to remind us. So starting with our y-intercept here, we can connect these two solution points with a smooth curve, extending infinitely upward, but never crossing that vertical asymptote. And this curve goes in the opposite direction as well, again, getting infinitely close to that horizontal asymptote, but never crossing it. Now, on the other side, again, starting with the ordered pair 3, negative 2, we can connect these 2 points with a smooth curve, and we can see that the graph is going to get infinitely close to that horizontal asymptote, but never cross it. And the same thing as we move downwards. That graph is getting infinitely close to the vertical asymptote, but never crossing that point. And here you have it. This is the graph of the given rational function, negative 2 divided by x minus 2.